Well, it's, of course, a rare privilege and an honor to be addressing you today in such distinguished company. We're here to celebrate Professor Dyson's, I'll say, 90th year, because this is not actually his birthday. Professor Dyson has his birthday on the 15th of December, but this conference is something like Trooping the Color, I think, for Professor Dyson. It's like the official Queen's birthday, except it's the King's birthday in his case. Professor Dyson, of course, he doesn't know it, but he had a very big influence on my own career. And let me tell you how it arose. When I was a student at Imperial College, the first graduate course we learned was, of course, quantum electrodynamics. And persons who taught us that course were two newly appointed lecturers. There was Tom Kibble and there was J.C. Taylor. And Taylor told us all about Dyson's wonderful seminal work on QED and the way to look at QED and renormalization, whereas Tom Kibble taught us the Schwingerian way of doing it with sources and functionals and so on. And also in strong interactions, Paul Matthews taught us about the Dyson Lehman-Yost representation of scattering amplitudes. So you see, he had a big role there. But this is not what affected my career. When I went on my first postdoc to, it would be in 63, 64 to Wisconsin, there was a member of staff there called Hal Lewis. And Hal Lewis always spoke, of course, very highly of Professor Dyson, and he would tell the following story, that Dyson would attend one of these summer schools, Berkeley or wherever else, and he would ask for a list of the most prominent physics questions. And this list would be produced, and then he would sit through the summer school and solve them all. I don't know how true that story is, but it certainly impressed me. In another way, he has also impressed me. It's the width of his interest and the fact that he does not follow the crowd. I think that's really quite important. And it's an inspiration to any young person. And especially when you go to the backwoods like I've done in Tasmania, you've got to learn to stand on your own 2 feet, and you should not try and follow the crowd because you're way behind the caravan and you'll never catch up. In order to do physics at the very forefront, you have to be there feeling the pulse of physics, as I did when I was at Imperial College. So I was really impressed by the way he operated, and I've tried to follow, be a very, very pale shadow of what he is, okay? So you see, I'm a great fan of his work, and what I will tell you about today, I hope you'll find a little bit interesting. It's very different from what other people do. The theme of my talk is to see whether you can unify electromagnetism and gravity in a way which is totally different from everybody else. Now, this is not exactly the abstract that appears in your booklet, but it encapsulates what I want to say. The idea is to think about events in a slightly different way from everybody else. So let me tell you how it goes. The origin of this idea goes back to supersymmetry, which I was very keen on earlier on. The next slide. Now, Professor Dyson has written a nice book on disturbing the universe. I don't think the universe needs any disturbance. It's automatically disturbed. Think of the opposite. Suppose the universe had no disturbances. It would be very boring. It would be a contradiction in terms. Nothing would be happening, and we wouldn't even be aware it was existing. So on the contrary, the universe has to evolve, and it's evolved by a punctuation of a number of events, like where it's happened, when it's happened, and well, this is where I want to concentrate. What has happened? I'm trying to make a geometry of where, when, and what. I mean, if you were a reporter and you say, oh, an event's taken place at Singapore airport, you say, all right, that's fine. Well, what event has happened? What event has happened is that there might have been an accident, a plane crash, the Beatles might have arrived. Who knows, yes? You want to know the what. And what I'm trying to do here is to put some mathematics into the what. there'll be a number of ingredients that come into the what. And these ingredients are going to come in through a number of anticommuting complex number. This is the way I'm going to introduce the what. Normally, when you do quantum field theory and you say something has happened, you put an interaction between a number of fields. These number of fields have labels on them. And what I'm trying to do is to put some mathematics into the labels themselves. I mean, for example, supposing you are eating cornflakes and bran flakes. If you have bran flakes, you have no sugar, you have no salt, yes? So sort of it's the unadulterated flake. On the other hand, you might be eating cornflakes, and cornflakes, the manufacturers put in a lot of salt and a lot of sugar because they want to save costs. But it tastes the same almost as a bran flake. So what happens is you can add features to the basic things. Once you've added saltiness, it's salty. Once you've added sweetness, it's sweet, and that's it. You can't doubly sweeten it. Well, actually, you can doubly sweeten it, but in my scheme, you can only have one. Once you put a characteristic or an attribute, that's it, you've got it. And you have, of course, the opposite attribute. And this is how the scheme is going to work. So let's remind ourselves about anti-commuting numbers and operators. Of course, operators have been known for a very long time, and we've used them a long time to describe electron and all the Dirac fields. But of course, the numbers themselves were only invented a long time ago by Grassmann, and he used them in differential geometry, but we didn't actually use them very much as numbers until about 1970, when the Becky-Rouet-Storer-Tutin symmetry for quantizing gauge-fixed theories came to the fore. And of course, in supersymmetry, they played an extremely significant role. And that's when the first time that we used anticommuting numbers, I'll call them A numbers, as well as C numbers. And let's remind ourselves about the difference between the two. In Bose-Einstein, you have plus, minus, commutator, anticommutator, this factor here in statistics, the other factor. This is an interesting thing here. If you integrate over real commuting numbers with the square of the Klein-Gordon operator, you get the inverse of the determinant. If you do it in the Dirac case, the complex one, you get the plus one. In other words, they work oppositely on the determinants. And this is confirmed by the group theory. If you look at the representations of the groups, the O2n group, if you change n to minus n, you get exactly the same results. So this is kind of telling you that the number of dimensions of the bosons and the fermions act in completely opposite ways. This is, of course, very well known. If you're doing BRST symmetry, you use Lorentz scalar, and if you're doing gravity, you'll have to use A numbers which are vectorial, as Feynman showed, and you have pairs for ghosts and anti-ghosts. Whereas if you're using supersymmetry, you're going to use Lorentz spinors. And if you're doing the gauge theories and you use BRST, it's good for getting renormalizability of the theory. SUSY has been around a long time, and it's very attractive theoretically, but nature has not confirmed it. Unfortunately, even the Large Hadron Collider has shown no signs of it. It's a bit like waiting for Godot, all right? There are no signs of supersymmetric particles or states. It saddens me in a way because I loved supersymmetry, but now I'm afraid I'm disenchanted with it. So I've made a confession already, okay? Now, the main theoretical attractions of supersymmetry, of course, is it's the consistent, non-trivial higher group incorporating Poincare. Yes, indeed. It unifies bosons and fermions. Brilliant. This is, I think, its most significant feature, the cancellation between the infinities of the boson and the fermion loops, and that improves the renormalizability enormously. And then people go along various tangents. This is the next tangent. They found a lovely supersymmetric generalization of gravity. It's called SUGRA. And it even allows internal symmetries to be incorporated through the generators, where you extend these Q's to various labels like n equals 4 Yang-Mills or n equals 8 supergravity and so on. And it allows for even generalizations to strings and branes. Now, Gell-Mann came in 1974, and when I was playing around with this idea here, which is to attach various labels to the supersymmetry operators. And he was interested in my work, and we had a chat, and he quickly disillusioned me and said, sorry, but this idea will not fly because it'll mean that your states will bring in spins as well. Ooh, I better keep away from this. It'll bring in spins as well, and you're going to get a lot of spin proliferation. So I was easily dissuaded from proceeding along those lines, and it goes into the subconscious, and you forget about it and you go on to do other things. But now I've tried to resurrect these ideas, and I'm going to try and tell you about where we go from there. Let me remind you about these negative dimensions. Every time you have a Bose field, gone too far. Every time you have a Bose field, and if you have NB Bose fields, you get d. Actually, you get d to the minus NB. And if you have a Fermi object, you have d to the power NF. So you can construe the commuting coordinates as adding to dimension, and the anticommuting coordinates as subtracting dimensions. And as I said, this is confirmed by group theory associated with the representations of Casimir's, the ON and SP2N as it is. It's as though the Lord giveth and the Lord taketh away, all right? So, if you can match the number of C coordinates with the number of A coordinates, you might actually get a situation where you get 0 total dimensions. And this is something which will appeal to, I think, Leonard Krauss. He's always said that the vacuum is abhorred by nature. Zeros unstable. And this is how I would generalize this to actually include dimensions. So to the 4 space-time coordinates, I'm going to add 4 anticommuting coordinates. I'm using Roman letters for space-time. I'm using Greek letters for these extra coordinates that you add, okay? And to get this, now actually I'm going to use 5, but I'm going to use half the states, so it's effectively like 4. So the idea is I'm going to associate these Lorentz, they're now Lorentz scalar anticommuting numbers. I'm going to associate them with the attributes of an object, a property, like saltiness or sweetness or whatever it is, okay, if you want to add. And in fact, I'm going to have 5 of them, and these I'm going to label them zeta 0 up to zeta 4, and the charges of these guys are 0, this 1/3, 1/3. These are like anti-D quarks. This is like the neutrino. This is like the electron. And they have various Fermi numbers. And I'm going to build up properties out of composites of these objects. The whole idea of this is to get the generation problem understood. That's the whole reason, the inspiration for it all. As you know, Isidore Rabi said, when the muon first arrived, who ordered that? Well, of course, the tau lepton is another one of these guys. Well, I will tell you, these partners of the electron, they're on the menu anyway. Let me show you how this works. I still haven't got to, this is just the entree. I'm going to talk about the main course in a little while. The idea is to, if you have a superfield, you've got to stick to spin statistics. So what I'm going to do is, I'm going to expand a Bose field into even powers of these, because you remember these anticommuting objects, okay? So they have zeta bars to power ZR and zetas to power Z, and there are various expansion coefficients like this. So if it's a Bose object, you'll have even numbers of these. If you have a Fermi object, you'll have odd numbers of these. And these 5 properties, which I'm going to use, no accident 5. SU5 is a very nice compact theory, even if it isn't unified in a grand way, but it's a nice way of collecting all the groups of particles. So what I'll do is I'll label the 0 label to denote the property of neutronicity, the label 4 to be the label for electricity, and labels 1, 2, 3 for color or chromicity. It's not an accident. These groups are automatic in this scheme. SU5, SO10, they're all contained in there. Now, as I said, I have to halve the states because I've got too many of them. And what I do first of all, I really need to show you the next slide, where I expand the fields in powers of their zetas. Remember, the expansions all stop. We are dealing with anticommuting numbers, so they won't go on forever. Okay, so in particular, let's go back to the previous one. What I'm going to do is I'm going to halve them by saying, well, if you, back, yeah. If you reflect it about the main diagonal, you're basically getting the complex conjugate. You go from here to here. The stars are the complex conjugates. And if you reflect about the cross diagonal, you're doing a duality operation, essentially. This is how you halve the number of states. And in fact, these are the rules for doing it. If you change R bar and R, you get the conjugate. If you change 5 to R, if you change from R to 5 minus R bar and 5 minus, you get the dual, and the dual has the same charge and Fermi number, so that's fine. There's a rule for getting all these dualities. Once you've done that, then you get a certain number of states when you do these expansions, but you can impose anti-duality conditions to cancel some of them out, and indeed you can get rid of some really nasty things that you can get as combinations from this recipe, all right? And this is where I've just looked at the fermion, the quark fields, and this is where they lie. They lie in these corners. And what I want to point out is they contain all the known generations. It comes automatically. And they come automatically in the right groupings also. But there are differences with the standard model. I think that's a good thing, because when there are differences with the standard model, it means you can actually say there's something wrong with it. Let me tell you what's wrong with it. If you look at the first generation, in the first generation, you have product of 2 of these anti-Ds with neutronicity, and then here's the doublet. Look, U1, D1, zeta 0, zeta 4. And the color is there, okay? The colors are in these 2 things. If you have the second generation, you have this, and with the zeta 4 bar, zeta 4, and zeta bar, zeta 0. But if you look at the third generation is different. The third generation has, this is the U-type quark, this is the D-type quark, and wait a minute, there's another one. It's actually a triplet. So the scheme gives you something which is 2 doublets for the first 2 generations, and then a triplet for the third one. So I would suggest that the best way is to actually see if you could determine this last quark, and well, I don't know what its mass is, but the best way to look for it is through E plus, E minus annihilation is my guess, all right? And the CKM matrix, because of this third one, is not going to be exactly unitary. So there are certain predictions that come out of this scheme. Now you can treat the Higgs fields in much the same way. The Higgs fields lie in the blanks here, the blank corners here, here. That's where the Bose fields lie. And if you see where they lie, there are actually 9 Higgs fields in this scheme. It's predictive again. There's the standard Higgs doublet, which is a combination of 4 of these zetas. And there are a lot of other uncharged runs. So there are lots of Higgs fields in the scheme. These are the brothers that Pong Chang suggested. But they're well specified. You don't just invent what you want. You've got to take what you're given here, all right? And the others are obtained by duality. Now, I told you this was the entree. This is actually the introduction. What I want to tell you is something much more interesting, which is what happens if you try and geometrize all of this. Sorry? No dynamics, absolutely. Yes. I'll put the gauge fields in now.
I don't see how you identify these with the particles that we observe without knowing.
We have to have the gauge fields, absolutely. Yes, you have to have the gauge field. So let's see where the gauge fields fit into this. Well, you can gauge the theory very simply. All you do is...
For example, those bosonic fields we discussed.
Yes.
They're all what we would call Higgs.
Yes. They're all part of one super Higgs. Sorry?
256 Higgs.
Well, no, uncharged ones, there are only 9. There are only 9 uncharged ones. Okay? So where are the gauge fields? Now, you can do the usual thing, which is to say, well, all you've got to do is to make sure it's in covariant under gauge transformations, which means attaching derivatives with the generators. The generators of the group are given by zeta d. They're like shapeshifters, these things here. In the same way that d by dx is a position shifter, d by d zeta is a property shifter or a shapeshifter, all right? But you can always do that. But there's a much better way of doing it. And this is what I really want to talk about. There is a possible way of, which is fully geometrical and which incorporates gravity. And this is what makes it an interesting concept. I want to construct a fermionic version of Kaluza-Klein theory without having the terrible properties the terrible problems of dealing with infinite modes. There are never any infinite modes if you're dealing with fermionic objects, okay? And so what I'm going to do is I'm going to enlarge my framework, if you like. That's what you call the framework, I think, David, which is to add to X the property. So this is the where and the when, and this is the what, okay? Now, in order to succeed in this idea, you have to introduce a fundamental length. The point is the separation is now going to be a separation in place, in time, and in property. So what happens is, because these property coordinates have no dimensions, you have to introduce a length scale. You're stuck with it. So what I'll do is I'll introduce a length scale to tie up property with space-time. And actually, it is connected with the gravity scale, as it turns out. So the gravity part of the force, which falls in the XX sector, the gauge fields, this is where the geometry comes into it. The gauge fields lie in the X, the space-time property sector, and the Higgs scalars form a submatrix in the property sector. Now, the maximal gauge group you can have actually is SU5, but it turns out that nature doesn't want SU5. It wants SU3 cross SU2 cross U1. So as far as gauging goes, it's only subgroups that seem to be gauged, and I have no idea why the larger SU5 is not gauged. I'm not in a position to argue that point. The gauge transformations are going to be regarded as property rotations dependent on space-time. Good, this is the obvious thing to do. In this scheme, because these auxiliary Z labels are Lorentz scalar, there is no place for a gravitino. I'm sorry, no gravitinos, no spin. And there's necessarily a finite number of modes. So we now have to generalize relativity to include A numbers. And we spent a lot of time trying to do that right. And we have got it right. I can declare that. What we're going to do is the enlarged coordinate is going to be called XM. I use capital letters for the enlarged space-time. And if it happens to be space-time, I'll use a Roman letter. And if it happens to be an anticommuting label, I'll use a Greek letter. And I'm going to set a grading which is 0 for space-time and -1 for this property. So if you have two of these vectors, shall we say, you get a minus sign if they're fermions, and you get +1 if they're boson Fermi. Okay, so that bit's easy. Now, if you want to do general relativity, you have to be very careful now with your ordering and your sign factors. This is what can stymie you quite easily. Now, my student is actually very good at doing these things. This Paul Stack, who's my co-conspirator, he's been able to marry his good understanding of physics with a good understanding of computers, and he has been able to do an algebraic computer program to check painful human things and try and eliminate errors. And I think we've got all the factors right. Now, the idea is we have to set the notation. So what we'll do is we'll always take left derivatives. We've always been taught to take derivatives on the left. I'm not going to bore you with putting right derivatives just to confuse you, all right? So they're all left derivatives. Unfortunately, if you look up any books on relativity, unfortunately, they always put the derivative on the right. A(n, n) is meant to be this thing, although you've done it on the left. So what you must not be surprised is to find some sign factors turning up in all of this. Okay, so just beware, there will be some sign factors, and it's natural because we are stuck with the two well-established notations, left derivatives and the comma convention for taking derivatives. Well, you can see by the transformation laws of vectors for contravariant and covariant vectors, leaving this as an invariant and so on. I'm going to skip through a lot of the details here, but you have to get these all right, by the way. And we have agonized over these signs. If you have a tensor, you've got to make sure you've got the right sign factor here for the transformation of a tensor, like, for example, the metric. Look carefully at the way the indices are summed. This goes against this, which kind of cancels it out, and this goes against this, which kind of cancels it out. So you get an overall scalar. And likewise, you can raise and lower indices. You have to be very careful how you do these things. And if you look at the inverse of the metric, this is a metric, and you take the inverse and get the unit matrix. If you swap these labels around, you get a -1 to the power, actually ml, but it's the same as m. And this is a well-known factor. This factor here says that if you have to sum over Bose objects from taking a trace, and a minus sign for the Fermis. This is very well known. Now, this metric tensor is graded symmetric. If you swap the indices, you get a minus sign if it's overall fermionic. And if they're both fermionic, you get a minus sign. And otherwise, you get a plus sign. Once you establish these rules, you can then go on and work out covariant derivatives and whatnot. Okay? You can work out covariant derivatives, and you can establish the rules for covariant differentiations. You get a Christoffel symbol, and the Christoffel symbol, which is given, this is how it's given in terms of the metric. They have all these stupid little factors, but you've got to get it right. And these are the factors. And once you've established the rules for covariant differentiation, you can go on and work out the generalized Riemann tensor, of course. And to work out the generalized Riemann tensor, you've got to take a plus sign. When you swap these two indices, you've got to take a plus sign if it's fermionic. Otherwise, it's the usual minus sign. So you can work it all out. And you can work out the Riemann tensor in terms of the Christoffel symbols, and that's what it reads. And as a check on all the work, you can then work out the fully covariant Riemann tensor by lowering the index, and look at the rules for it. It checks perfectly. It's absolutely right. If you swap the first two indices, you get a plus sign if it's fermionic. Otherwise, you get a minus sign. Likewise, if you swap the last two, and if you swap the two pairs, you get this factor here. You can also establish the first Bianchi identity in this enlarged space, which is this. Look, it's easy to glaze over these. Once you see one formula after another, it's easy to go to sleep, all right? But these are important formulae, in fact. You can also work out the second Bianchi identity, which is a differential one, a cyclic differential one here. And this is the actual rule for it. And once you have understood what the Riemann tensor behaves like, you can then form the Riemann the Ricci tensor by contraction, and it has also the property that it's graded symmetric. And you can work out the superscalar curvature, which is the fully contracted one here. And it's interesting that if you actually apply these contractions to the differential Bianchi identity, you come out with the generalization of the Einstein tensor. And this is what it is in this enlarged space. It all comes out and drops out beautifully. Okay, this is this is only framework so far. There's no theory yet. Okay, so let's see where the theory comes into it. Let's look at a flat space-time and property. In flat space-time and property, the length is Minkowskian and it's sort of symplectic and flat in this space, in the zeta space. And notice that the analogues of these, the eta tensor, has to have the factor L squared over 2, because there's got to be a length, this separation. Now you can curve the space by writing a number of frame vectors, and you want to make sure that you kind of mimic Kaluza and Klein. And it turns out the number of you have a number of frame vectors that you can get to obtain the metric tensor. And when you do that, this is what the metric looks like. You see, it is actually very similar to Kaluza-Klein. In the space-time sector, you get the metric tensor. You also get, this also happens in Kaluza-Klein, you get the electromagnetic field turning up here. The space-time property metric, if you think about it, you can't have anything else. You can't have anything else because it's got to be vectorial. It has to be anticommuting, so it's got to be something like this. And if you look at the property metric, now what are these C1s and these C2s? In principle, you can actually add property curvature to this. These act like mass terms in the Schwarzschild metric. They're very similar to that, except it's in the attribute sector. Now, I'll just make a few observations about this. The charge coupling always accompanies the electromagnetic potential. The constants Ci provide property and phase invariant property curvatures, just like mass, Schwarzschild. And there may be expectation values of Higgs fields. And finally, this intrinsic length scale, which you have to have there, no choice. Okay, so what are the features of this? Well, there are no gravitinos, because these fields would carry a spinor index that spoil everything. But actually, you could include other things in the metric. You couldn't, if you were to quantize the theory, you could allow yourself an object like a ghost field in the property space-time sector. And in fact, you have to have that. And you can likewise include if you want to quantize the theory, you have to include the two ghost fields in the property sector. So I'm not going to do quantized theory, just semi-classical theory, all right? So anyway, once you've got your metric, you can then go on and determine its inverse. And now it's just a matter of cranking the handle. That's all you've got to do. And see what you get. And some very nice things turn up. I'm not going to give you a list of the Christoffel symbols. It's just going to make you go to sleep. But what you have to do, certainly, is to work out the analog of the square root of the determinant, because that's going to come into the action. You have to do that. So the analog of the determinant is going to be something like, it turns out to be this. It's related to the property curvature times the usual metric tensor. Or you should take the square root, but anyway. I want you to notice that the gauge potential is absent. Now, once you've done that, you can then work out the gauge changes as property transformations. That's all they are. It's not surprising at all. All you've got to do is to phase out the properties and the anti-properties. And if you look at just the general transformation rules for the metric tensor, you find that it's just a gauge transformation. That's all this is, nothing else. Not a surprise at all. And you can look at, in fact, all the components of G, and they all are consistent with this. So what happens is that the upper components of G remain unaffected and gauge invariant. The lower components of G, the covariant ones, are gauge transforming. The same comments apply to the covariant Riemann-Ricci tensor and the contravariant. So what can we do now? Well, we can work out surely what Einstein would have done, which is to work out this full superscalar curvature. Let's do that. So what you do now is you take your, we know we have all the symbols now. We've got the gammas, the g's, everything. We just simply sit down and turn the handle and see what you get for the Ricci tensor and for the superscalar. And if you sit down and do it, and it takes a bit of work, and this is where the computer program done by my student comes in useful. He can check my work, and it checks out, and I can assure these numbers are right, and I'll bet my bottom dollar there's no mistakes on this. So what you get is that the upper Ricci tensor is this is an interesting result because it gives you a cosmological term, all right, possibly, and you get a product of the two Maxwell tensors. And if you look at the superscalar curvature, it reduces down to this. So what I'm going to do now, I'm going to neglect superscalar. I'm going to neglect space-time curvature. We've got to do baby steps before we can run, all right? So what we'll do now is we'll integrate over to see what the Lagrangian is. You have to integrate over property. So what we're going to do is we'll take our superscalar curvature and integrate over property. This is like you do integrating over x and over t. It's the same thing. And if you sit down and do it, lo and behold, there it is. You get the Maxwell Lagrangian, and you get a cosmological term. And if you go further and work out the Einstein tensor, which is what you really need to do, you get an amazingly beautiful result, which is that you get a cosmological term. You get the stress tensor automatic. You don't have to do any work. It just drops out. The electromagnetic stress tensor is then part of this, okay? Part of the Einstein tensor.
Why don't you give it Dilaton?
Sorry?
Why don't you give it Dilaton?
Yeah?
Dilaton.
Well, that'd be the next stage. You can put a dilaton into the theory.
You should get one
Well, I think there is room for improvement in all of this. Certainly, yes. You might be able to get one if you put in more information in the elements of the frame vectors. I think if you make them fields, then you will get dilatons. If you include gravity by curving space-time, you get the Einstein curvature, you get the electromagnetic term, and you get a cosmological term. And you can just identify them, and I've identified them. And in particular, if you look at the full Einstein tensor, you get the full, this is the super Einstein tensor, you get the ordinary Einstein tensor, you get the electromagnetic contribution, and you get a cosmological term. Normally what's done is that you say that this is equal to this on the other side. That's what you do. But this now becomes part of the geometry. Now, this has problems, though.
So what are the C's?
Good question. What are the C's? Well, the C's are what determine the constants here. Let's have a look. If you look at the Newton's constant turns out to be given by this. Of course, it's a positive number. And the trouble is, once you put in this thing here and C1 is positive, what happens is the cosmological term goes negative. And you say, oh my goodness, what have you done? And it's a small positive constant, in fact. What is probably worse, it has an enormous number. Now, anybody who does particle physics is always stuck with this 10 to the minus 120, which the people who do astrophysics find from expansion of the universe. I think we're all stuck with it. Now, it is possible that by adding further properties, we can change, I'm pretty sure we can change the sign of lambda and And we can make it easily we can make it 0, no problem. But to make it equal to 10 to the minus 120 means making it very fine-tuned, and I have absolutely no answer to that question. Absolutely no answer. What we're trying to do at this stage is to extend our work to electroweak theory, to geometrize electroweak theory, and we don't really anticipate any conceptual problems, only complications, all right? Oh, I finished. Okay, I finished. Now, it could be that all these ideas will bite the dust. I've seen theories come, and they've seen them go also, and sometimes they get resurrected again. It could be that everything will go to pot. At the moment, we're quite happy with the way we're proceeding. And if I end the talk by saying, spinor supersymmetry is dead, scalar supersymmetry is long-lived scalar supersymmetry. You can now put me in stocks and throw your ripe tomatoes at me. or burn me at the stake or whatever, because I'm a heretic in that, from that point of view. Okay, thank you very much for your indulgence.
I have left 2 minutes more for the discussion during the talk.
Thank you.
Please.
First, let me say that I'm very glad that you did this, because a long time ago, I and Kaplansky tried to do this, but failed.
All right.
So I don't know how you succeeded, but I'm very glad that you did it. Okay.
I'll bet my bottom dollar this is actually correct, all right?
Yeah. Oh, okay. I trust you. So, but anyway. So in your case, this fermionic coordinate are like fiber bundles, okay?
Yeah.
In Colbert-Klein picture.
Yeah.
But you can also introduce the real. You can extend the space-time coordinate, space-time dimension, and you could also that will give you the standard Colbert-Klein, okay?
You could.
And so in your case, the space-time symmetry is Lorentz plus SU5. Did I understand correctly?
Correct. In the flat case, it would be Lorentz plus SU5, yes.
So...
you have general relativity is there.
Yeah.
Yes.
So I'm still... or I trust you, but...
I have the papers here, you can read them.
There is a no-go theorem.
Mm-hmm.
There was a generalization.
Yeah. Yes.
So how do you avoid that no-go theorem?
We don't even, doesn't affect us at all. We've separated the fermions from the bosons. It's nothing to do with one another.
Yeah, but I thought that violated locality, spin
We
statistics.
haven't violated any principle as well.
Well, you don't, I mean, I haven't seen a theory. You have could you write down, for example, without gravity, L Planck equals 0, right?
I can have a theory without gravity, yes.
Yeah, I mean, so that complicates matters enormously, very difficult to follow, and usually the discussion of the maximal space-time symmetry groups, you know. There is this famous, who is it, Becky, I'm confused, I can't remember now.
Well,
But as you remember, supersymmetry was a counterexample to the Coleman-Mandula
Yes,
theorem,
indeed.
and then there was an improvement on that that allowed for
Yeah.
supersymmetry,
Yes,
but nothing else.
yes.
And this seems to be something else. So I was waiting till you got beyond just free fields.
This is just a direct product of an internal symmetry and gravity, that's all it is.
Oh, so what is the internal symmetry?
Well,
Forget about gravity, just the standard model. We don't have gravity.
It's just the standard model. I haven't got any.
No, but you had a lot of other things.
No, but I haven't gauged them. The only thing gauges...
You can't gauge anything without
I
gravity
can
in your
gauge.
theory?
I can gauge a lot more, but the experiments tell me don't gauge SU5.
No, but you can gauge any... can you consider a theory without gravity?
Yes,
Oh, okay. With any gauge group you want?
yes.
So what's the difference?
Well, it has to be symplectic group, first of all, because the gauge group is associated with these zetas, all right?
So without gravity, you should be able to have the grand unification.
Well, you could in principle have it, yes. I haven't grand unified it. I've just stuck to the standard model.
So how or what determines the number of the fermionic coordinate? Is this arbitrary or?
No, I had to choose the minimal number that will encompass the known particle spectrum. That's what's left.
So you could
Five
also
came
extend
from
it.
SU5.
Sorry?
5 had to do with SU5.
Yes, of course it does. Yes, and SO10 as well.
But I was wondering why you have 5, not 4.
Well, I couldn't get by with 4. That's the simple answer. 4 is insufficient to get all the known.
5 is the minimum. 5 is the minimum.
5 is the minimum number I needed. Yes, correct.
You mentioned something about the quantum aspect of this kind of a problem. Say,
Yes,
quantized gravity.
yes. It is possible to include it in this scheme. I have not included it.
There's no more Philibine, constraint of Philibine.
Yes, you have field binds, yes.
How about the possibility to extend your idea to work a real skirmion model?
Oh, I don't know. You're welcome to try. I don't know. You might be well right. I just don't know. You might get some things along those lines.